Actually, vector differentiation and vector operators. This is the related to that chapter. The topics are vector differentiation means a function has in direction. Generally, the function f of x comma y, whatever it may be, it is in algebraic expression. Either it is x square plus y square. This is a function, but it is not a vector function. It is the algebraic function. If the function can be taken in the direction, whatever it may be, either two-dimensional or three-dimensional or one-dimensional. So we are defined the function along with the direction, then the function is called as the vector function. Okay. In general, the vector function can be taken as f of t is equal to f1 of t into I plus f2 of t j plus f3 of t k. This is a three-dimensional function. In this, a function, this is nothing but f1 of t, f2 of t, f3 of t. These are algebraic functions in t variables. But these are the coefficient with the I, means the function go taking the direction along the x-axis. The f2 function taking the direction along the y-axis. F3 function taking the direction in z-axis. In the general situation, in the daily life, we are discussing the so many cases. Suppose that we can stay in a position that depends on the three-dimensional. Why? Because we are in space, spherical. So if either a point in the cube shape or cuboid in three-dimensional, suppose we are taking in the two dimensions, suppose we can stand in the any open place, that is also makes the direction. We are standing in the vertical line and the foot is there on the floor, means that is the horizontal line. Whatever it may be, the position of any person, position of any particle, position of any vehicle, whatever it may be, that position can be denoted as the function that in the directions. Through the direction means it is the vector function. In this also the limits and derivatives all are defined. In general, the limit of the function means we can take limit x tends to a, f of t minus f of a by t minus a is equal to some direction, that is the derivative of the function of t, that can be defined with the limit function. Okay, this is the derivative. The higher order derivative means the derivative is denoted as the higher order derivatives. In general, we can taking as the functional derivatives, how those we can take. In this also we can take the either these are the vectors or scalars. If a vector and b vector are the vectors and these are vector functions, differentiable vector functions, then these functions can be defined as the derivative of any variable if a and b are the functions in the direction of the variable t, means those two functions are called as the vector functions, vector point functions. The derivative of these two vector point functions, summation or difference of the two vectors, means the individual derivatives only, dA by dt plus or minus dB vector by dt. Okay, like that. If d by dt, how the in algebraic functions we can taking as the same way here also. If a vector dot b vector means it is equal to dA vector dot dt, dA vector by dt dot b vector plus a vector dot db vector by dt. If the vectors can be taken as the cross product, then a vector cross b vector is equal to, we cannot change the direction. In the dot product, no worry about the direction. Why? Because we know that a dot b is equal to b dot a. But a cross b is not equal to b cross a. Why? The directions will change. Here we can indicate the directions also. That is very important. dA vector by dt cross B vector plus A vector cross dB vector by dt. These are the derivatives. How the function can be defined and how we are taking the derivatives, what are the partial derivatives and the ordinary derivatives. Ordinary derivatives means we can take only single variable functions, then we can differentiating with respect to such variable is the ordinary differential equations or the ordinary derivatives. The partial derivatives means the same way the function can be involved in two variables, so then we can differentiate with respect to such variables. So such type of the differentiations are called as the partial differentiations. In this, the main concept is vector differential operator. Here, in general, in the algebraic expressions, we can take d by dt, d by dx, d by dy. These are the derivative operators. Okay, here we can take capital D only. Notations are capital D. That depends on the function can involved in which variable. Then the operator is also differentiating with respect to such independent variable. But here the vector function f vector is defined as f1i plus f2j plus f3k. Here, the function is in direction, vector position. We are discussing only for three-dimensional geometry. That is, in this, the extension of the three-dimension, n-dimension is also possible, but it is convenient to discuss the three-dimension. In the vector functions, we can take the operator. Operator is the vector operator. Vector operator is denoted by del. Del is nothing but I dou by dou x plus j dou by dou y plus k dou by dou j. If we can take any function, phi is a scalar function. Phi is a scalar function is nothing but suppose we can take the phi is a function can be involved in three variables x comma y comma z, then it is said to be the scalar point function. In these two types of the functions we are discussing here. One is vector point function, another one is the scalar point function. If it is with the vectors ijk, then that is called as vector point function. Without ijk, then that function is said to be the scalar point function. Okay.
Yes, ma'am.
In this, the vector operator del is the vector operator. Using of this vector operator, we can taking as the definitions of the gradient, divergent, curve, and directional derivative. Okay, with the vector operator. What is the vector operator? The vector differential operator is denoted by the del, and it is defined as I dou by dou x plus j dou by dou y plus k dou by dou z. Okay, this operator processes the properties. Those are ordinary vectors as well as differential operators. In that case, we are taking gradient, divergence, and curve. Here, what is the gradient of the vector? Gradient. Gradient means the vector operator is associated with a scalar function. Then that is called as the gradient of the gradient or gradient of a scalar point function. Here, the definition of the gradient or gradient of scalar point function. Gradient of a scalar point function means let phi of x comma y comma z be a scalar point function of position defined in some region of space, then the vector function I dou pi by dou x plus j dou pi by dou y plus k dou pi by dou z is known as gradient of pi, and it is denoted by grad pi or del pi. That is nothing but grad pi is equal to del pi equal to I dou pi by dou x plus j dou pi by dou y plus k dou pi by dou z. Just you can observe here. Here, this is a vector point function. After the taking the derivative, here we are taking the pi is a scalar point function. After taking the derivative of the vector operator, then we are getting the vector point function. You remember that gradient is a vector point function. Okay. Here also some properties are there on the gradient. The properties are the first one. You remember these properties. If f and g are two scalar functions, then grad of f plus or minus g is equal to grad f plus or minus grad g. This is the one property. Second one, the necessary and sufficient condition for scalar point function to be a constant if f is a constant, then del f becomes 0. Why? Because derivative of any constant is equal to 0. So we are getting the 0 vector. Why? Because del is a vector operator, f is a constant function, scalar function. After operating of del f, then we are getting the vector function. Third one, grad of fg is equal to f into grad g plus g into grad f. Fourth one, if c is a constant, then grad of cf is equal to c of grad f. Fifth one, grad of f by g is equal to g into grad f minus f into grad g by g square, where g is not equal to 0. Just u by v, uv forms only. Sixth one, let R vector is equal to, it is a position vector, xi plus yj plus zk. Then dr vector is equal to dxi plus dyj plus dzk. This will come in the problems. We are taking the position vector and the derivatives. These are the sixth point is related to all theorems, vector integration theorems. So you can remember this. That R vector is a position vector, that is xi plus yj plus zk. Then dr vector is nothing but that is the derivative position vector, that is dxi plus dyj plus dz. If pi be any scalar function, this is any scalar point function, then d pi is equal to dou pi by dou x into dx plus dou pi by dou y into dy plus dou pi by dou z into dz. That is nothing but d pi equal to I dou pi by dou x plus j dou pi by dou y plus k dou pi by dou z into dxi plus dyj plus dzk. Is equal to del pi dot dr. What is that? D pi is equal to
Hello.
hello,
Madam.
d pi equal to del pi dot dr. You remember this. Sixth one is very important. Why? Because this will come in the vector integration. But fifth one is that is we know that derivative of in ordinary differential, derivative of u by v du minus u dv by v square. And we know that derivative of any constant of x is equal to constant into derivative. It is uv form, derivative of uv, u dv plus v du. The all are related to ordinary formations only. But the sixth point is commonly we are taking in the theorems. Okay. This is the gradient of a scalar point function. Gradient means we can remember the del operator, vector operator can be applied only scalar point function. The other two, divergent and curl, can be taking on the vector point functions only. That is the main concept. Okay.
Yes, ma'am.
The directional derivative can be defined on the scalar point function. Suppose let pi of x comma y comma z be a scalar point function. It is defined throughout some region of space. We are taking the scalar point function. The scalar point function can be defined some region of the space. Okay, this function have a value. This function have a value pi at any point, but at that point the position vector can be taking through the origin. So that pi is a value. We can take the pi function value at p point. Then suppose that is nothing but O is the origin, P is the any point. The function can be through origin to P point. We can take the position vector, that OP vector is equal to R vector, whatever the function. but the position vector is r vector. In general, r vector is the position vector that can be taken as xi plus yj plus zk. So here, if any function can be defined in some region, at particular point the function has a value, that value can be calculated through the origin. That origin to value is a line. Through that line, we can take the vector point function, that is the position vector. OP vector is equal to R vector. Here, let pi vector plus pi is a scalar point function and delta pi is the small difference, and this difference be the value of the function with the neighboring point of another q point. This is a value at point q. Okay, then we can calculate the another position vector OQ also. Okay, here the OQ vector is equal to R vector plus delta R vector. Then PQ vector is equal to OQ vector minus OP vector. That is nothing but R vector plus delta R vector minus R vector get cancelled. We are getting delta R vector. So this delta R vector be the length of delta R. Delta R vector has the length. It is also some having the value. So we are taking delta R is equal to norm delta R vector. This is equal to length of the delta R vector. That is nothing but we can calculate P is a point at that the function value and Q is also another point that is near to the P point. Then the small difference that is nearby means very small difference is there in the scalar function. So in the position also the same scale position difference is also there. Then we are getting the PQ position vector, that is the OQ minus OP. We are getting the another vector. For that vector we can calculate the length, means that is the norm vector is the length. So here this delta pi by delta R, it gives the rate. Rate means differentiation. That is the position vector's rate that can be changes the pi function moves from one place to another place, P place to Q place. The limiting of this delta pi by delta R, as delta R tends to 0, then it taking as d pi by dr. That is nothing but it is the directional derivative. Directional derivative means we can take the derivative in the direction. Okay, in the direction means P and Q are the 2 points. Those 2 points can be taking through the origin the vector point functions. Through the origin we can take for P point position vector is OP vector, for Q point the position vector is OQ vector, and we can calculate the PQ point. Why? Because the P point to Q point the function can be moving in the small change. For that small change we can find out the position vector. The position vector is also the small change is there. We can take the derivative in the position of the small difference of the scalar point function, then that is the directional derivative of that function. So here clearly we can tell that delta pi by delta R is the rate at which pi changes when moving function P to Q. The limiting of this is equal to d pi by dt. This is called as the directional derivative of pi function. Okay. Simply we can define in the theoretical way. This is the how we can find out the directional derivative. But in the definition form, how we can rewrite it? Delta pi by delta r gives a measure of the rate at which pi change when we move from P point to Q point. The limiting value of delta pi by delta r as delta r tends to 0 is called, 1 minute, delta r tends to 0 is called the derivative of pi in the direction of PQ, or simply directional derivative of pi at P, and it is denoted by d pi by dr. Okay. How to find out the directional derivative means, note the directional derivative of a scalar point function pi at a point P of x comma y comma z in the direction of a unit vector E vector equal to E vector dot del phi or E vector dot grad phi. That is directional derivative of phi at P equal to E vector dot grad phi or E vector dot del phi. You have to remember this formula. Okay. Did you understand? The first problem is it depends on the operator, vector operator. How to we can take the operator for scalar point function. Here we can find out the del of x square plus y square z. First we can, what is the del? Del is a vector operator, that is dou I dou by dou x plus j dou by dou y plus k dou by dou z. Okay, then we can take here del is a operator as a partial with the position of the vectors, that is I dou by dou x plus j dou by dou y plus k dou by dou z of x square plus y square z. Then here we can write the separate terms, that is the multiple to each and every term. It is equal to I dou by dou x of x square plus y square z plus j dou by dou y of x square plus y square z plus k dou by dou z of x square plus y square z. Here with respect to x means I into x square differentiation is 2x. The second term will be 0 plus j into dou by dou y means first term is 0. Second one is y square differentiation 2y, z treating as a constant, plus k into dou by dou z means first term will be 0, the y square is a constant, z differentiation is 1. It is equal to 2xi plus 2yzj plus y square k. Therefore, del of x square plus y square z is equal to 2xi plus 2yzj plus y square k is a vector point function. Pi is a scalar. After derivative, then it will get the vector point function. Okay. Second problem, it is very, very important. Prove that del of r power n is equal to n r power n minus 2 into r vector. First, we can take the r vector. R vector be the position vector, that is xi plus yj plus zk. This r is a scalar point function, that is small r is equal to modulus of r vector, that is equal to under root of x square plus y square plus z square. Here we can squaring on both sides, then r square is equal to x square plus y square plus z square. Okay. Now what they are asking, r power n. First we can taking the partial derivatives of the r scalar function, that is differentiating with respect to x, y and z partially on r not vector r scalar function. Then differentiation is 2r dou r by dou x is equal to 2x. From this, dou r by dou x is equal to 2x by 2r equal to x by r. So dou r by dou x equal to x by r. Similarly, dou r by dou y is equal to y by r, and dou r by dou z equal to z by r. Okay. These are derivatives can be using in the vector operator of the scalar function r power n. Here del of r power n is equal to, del is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z of r power n is nothing but, that is x square plus y square plus z square whole power 1 by 2, that is n by 2. Is it clear? Here r is equal to x square plus y square plus z square whole power 1 by 2. When we can multiply, then it is multiplied with n by 2. So now we can differentiating. First of all, we can write the separate terms. I dou by dou x of x square plus y square plus z square whole power n by 2 plus j dou by dou y of x square plus y square plus z square whole power n by 2 plus k dou by dou z of x square plus y square plus z square whole power n by 2. First of all, we can find out the first derivative, either x, y, z. Then we can write similar way. Why? Because the all expressions are same. X square, how the expression is that same, y square, z square is also like that. So here we can find out the dou by dou x is dou by dou x of x square, x square plus y square plus z square whole power n by 2. It is equal to n by 2 into x square plus y square plus z square whole power n by 2 minus 1. Again, x differentiation 2x. It is very lengthy. Just I can explain in another way.
Right, ma'am.
This is into r power n only. That is equal to I dou by dou x of r power n plus j dou by dou y of r power n plus k dou by dou z of r power n. It is equal to I into r power n differentiation is n r power n minus 1 into dou r differentiation is dou r by dou x plus j into n r power n minus 1 into r differentiation dou r by dou y plus k into n r power n minus 1 r differentiation dou r by dou z. Here in the place of dou r by dou x we can substitute n r power n minus 1 x by r plus j into n r power n minus 1 y by r plus k into n r power n minus 1 z by r. Then this r is taken to numerator, then n r power n minus 2 xi plus n r power n minus 2 yj plus n r power n minus 2 zk. Taking common n r power n minus 2, the remaining terms are xi plus yj plus zk. This is equal to r vector. So n r power n minus 2 into r vector is equal to del of r power n. It is the proof. Got it? They have given a, b, c or the scalar point functions. So we can find out the grad a, grad b and grad c. And its volume is nothing but we can take in the determinant of three vectors. Okay. Here grad a is nothing but del a. A is a scalar function, that is I dou by dou x plus j dou by dou y plus k dou by dou z of x plus y plus z. Directly I am doing I into dou by dou x of x plus y plus z plus j into dou by dou y of x plus y plus z plus k into dou by dou z of x plus y plus z. It is equal to I, x differentiation is 1, remaining or 0, plus j, y differentiation is 1, remaining x and 0, x and z are 0, plus k, xy differentiations are 0, z differentiation is 1. It is equal to I plus j plus k. This is the grad a vector. Sorry, not a vector, grad a scalar. This is del a. Next to find out the grad b. Del b equal to I dou by dou x plus j dou by dou y plus k dou by dou z. B scalar point function is x square plus y square plus z square. Write separate terms. It is equal to I dou by dou x of x square plus y square plus z square plus j dou by dou y of x square plus y square plus z square plus k dou by dou z of x square plus y square plus z square. It is equal to I x square differentiation is 2x, remaining terms differentiations are 0, plus j x square z square differentiations are 0, y square is 2y, plus k x square y square differentiations are 0, 2z equal to 2xi plus 2yj plus 2zk. Therefore, grad b is equal to 2xi plus 2yj plus 2zk equal to del b. Next, grad c. It is equal to I dou by dou x plus j dou by dou y plus k dou by dou z, or xy plus yz plus zx. It is equal to I dou by dou x of xy plus yz plus zx plus j dou by dou y of xy plus yz plus zx plus k dou by dou z of xy plus yz plus zx. Differentiate I. X differentiation is 1 into y plus 0 plus z into 1 plus j. Y differentiation is 1 x into 1 plus 1 into z plus 0 plus k into xy differentiation is 0 plus z differentiation is 1 y into 1 plus 1 into x. It is equal to y plus z into I plus x plus z into j plus y plus x into k. This is grad c. This is del c. Now we can find out the volume of grad A, grad B, grad C. That is nothing but determinant of three vectors. In three vectors, I, j, k are there. I components are 1, 1, 1. For grad B, 2x, 2y, 2z. For grad C, y plus z, x plus z, x plus y or y plus x. It is equal to 1 into 2y into x plus y minus 2z into x plus z plus 1 into opposite. If we take here minus, then AD minus BC only, minus 2x into x plus y minus 2z into y plus z plus 1 into 2x into x plus z minus 2y into y plus z. It is equal to 2xy plus 2y square minus 2zx minus 2z square minus 2x square minus 2xy minus into minus plus 2zy plus 2z square plus 2x square plus 2xz minus 2y square minus 2yz. If any get cancelled, minus 2z square plus 2z square plus 2x square minus 2x square minus 2y square plus 2y square plus 2xy minus 2xy plus 2zx minus zy minus 2yz plus 2xz minus 2zx. All will get cancelled. It is equal to 0. Therefore, volume of grad A, grad B, grad C equal to 0. Okay. These are the related to the directional derivative operator. Sorry, not directional derivative, vector operator. Tomorrow I will discuss directional derivative problems. Okay. These all are related to vector operator. Shall
Yes,
I
ma'am.
give homework?
Yes, ma'am.